Hello everyone. I want to talk in this video about the spreadsheet or the spool lifting analysis that I developed. In this spreadsheet, you use the sling length as an input, not an output. So you can use the slings you have in stock. Now, how can the program work? How can we get the pickup point when we have the sling length as an input? Look at this graph. You enter the spool dimensions and weight. The program calculates the COG, and then you give the program a suitable hook height. Then the program identifies the hook point. This hook point is considered in the program as a center of a sphere. So if we can imagine that we have a sphere which has a center in the hook point and a radius of the sling length. So this sphere or the sphere surface represents all the possible points that the end of a sling can assume if it's extended from the hook point to anywhere else, including the intersection points with the spool piece. Now, the program's job now is to find the intersection point between the sphere and the spool piece, which represents the the pickup point, and this is done by solving simultaneous nonlinear equations. So this is basically the idea, and let's now go to the program to talk about how can we do that.
So here, as you can see in the program, we have the spool dimensions, which is entered through this window, and the weights of the steel and concrete and all that stuff is entered through this window. This is a COG, and this is a coordinate system. This is a plan, and this is the elevation graph. So now let's add slings, which is the most important things. Let's add the first sling here. Okay, another one. Okay, fine. Now let's try something. Let's try for sling number one here. Let's make it shorter. We mark it here like this and make it shorter. As you can see, the attachment point is moving around as we reducing the length of the sling, because in each click of these clicks, the simultaneous the nonlinear equations are solved simultaneously to get the attachment point, as we explained in the beginning of the video. So this is the idea of the thing. Now let's try to get the tension. The tension should appear in this space here. We press tension like this, we get tension values. Of course, if we change the configuration and make it unstable, let's try to do something. Let's try to reduce the length of this one to become here and press tension again. It gives us value, which means it's still stable. Okay, let's do one thing. Let's remove one sling and get the tension. We press tension here. We didn't get any values because, as we expect, there is this configuration is not stable. We have sling here and another one here. We should have something here or here. So let's add another sling, and let's increase the length of this one a little bit and get some tension values. Tension, yes, we get tension values which are all are positive, which means this configuration is physically stable and each sling is loaded with a certain amount of load. Now let's try to reduce the hook height. This is hook height. Let's try to reduce it. As you can see, as we reduce the hook height, the slings are spreading out because it's the same idea. We are reducing the hook height, and the attachment point is is forced to be far away from the center of gravity. The same thing or the same idea if we increase the hook height. If we increase the hook height, as you can see, the attachment points are converging. And of course, let's get this link the other way. And of course, the tension values changed and everything's changed. Let's try if to see if this configuration is stable or not. Okay, there is the tension values, but one of them is 5.7 and one of them is 0.1 ton, which means this configuration is not very good configuration. The good thing we can do is we can get this attachment point far away a little bit and press tension again to get the tension values. This is more reasonable. This is how we work on the program. As you can see, this is the plan and this is the elevation, and everything is done very easily and very quickly as well.